This video is brought to you by mywayteaching.com.
Now let us study about the important topic, that is Carnot Engine. Okay, suppose you just consider we have a hot reservoir at temperature T1 and a cold reservoir at temperature T2. Okay, at temperature T1 we have cold reservoir at temperature T2. Then, what is the maximum efficiency possible for a heat engine which is operating between two reservoirs? So, what cycle of processes we should be adopted to achieve that maximum efficiency? All those things will come under this topic. Okay. See, this Carnot engine, s- it was discovered by a French engineer, that is Sadi Carnot. First considered this question in 1824. Then Carnot arrived at the correct answer even though the basic concepts of heat and thermodynamics had yet to be firmly established during those days. So we expect the ideal engine operating between two temperatures to be reversible engine. Irreversibility is associated with dissipative effects and even with lowers efficiency. It lowers the efficiency, isn't it? And we also studied that a process is reversible if it is quasi static and non dissipative. A process is not quasi static if it involves a finite temperature difference between the system and reservoir. So, this implies that in that reversible heat engine operating between two different temperatures, heat should be absorbed isothermally and it should be released isothermally. Then only we know it is we have identified that in two steps of the reversible heat engine: isothermal process at temperature T1 absorbing heat Q1 from the hot reservoir, and another isothermal process at temperature T2 releasing heat Q2 to the cold reservoir. To complete a cycle, we need to take the system from temperature T1 to temperature T2, then back from temperature T2 to T1. Okay. A little reflection, it shows that we can only adopt reversible adiabatic processes for these purposes which involve no heat flow from any reservoir. So if you consider some any other process which is not adiabatic, say it is an isochoric process, to take the system from one temperature to another, we shall need a series of reservoirs in the temperature range, that is from T2 to T1, to ensure that at each stage the process is quasi-static. But here we are considering a reversible engine which operates between two temperatures. Okay, and adiabatic process must bring about the temperature change in the system from T1 to T2 and T2 to T1 to complete that one cycle. A reversible heat engine operating between two temperatures is called as Carnot engine. Okay. Okay. This is called as Carnot engine. You can see in this particular figure we have taken the working substance of the Carnot engine to be an ideal gas. So how it works? You can see in this step 1, isothermal expansion of the gas taking its state from P1 V1 T1 to P2 V2 T1. So this is the first step, that is isothermal expansion of the gas. Here the heat is absorbed by the gas from the reservoir at temperature T1. It is given by the equation also. So this is also work done, that it changes from W1 to 2 by the gas on the environment. So we can write that equation as Q1. And in the step 2, as you can see in this figure, adiabatic expansion of the gas takes place. From P2 V2 T1 to P3 V3 T2. So work done by the gas, we can write it as W223. We have studied these equations before. Then in the third step, isothermal compression of the gas takes place here. From P3 V3 T2 to P4 V4 T2. So heat released Q2 by the gas to the reservoir at temperature T2. This is we can also write it through the equation, that is work done on the gas by the environment and in the fourth step, adiabatic compression of the gas again. Adiabatic expansion, now adiabatic compression from P4 V4 T2 to P1 V1 T1. So in that case, work done on the gas, we can write it as W421 mu R T1 So, total work done by the gas in one complete cycle, we can represent it with W, that is W122, So if you simplify the equations, the above equations that we have what I have done from 1 to 4, we'll arrive at the simpler equation, or we can say simplified equation. This is the equation. In that case, the efficiency of the Carnot engine is given by W by Q1. We already know it can be represented with 1 minus Q2 by Q1, isn't it? So, that is, we can write it since 2 to 3 is an adiabatic process. We know in adiabatic process how the equation, and we can take V2 by V3 out, and we can write T2 by T1 1 by gamma minus 1. Okay, and similarly if you consider step 4 to 1 is an adiabatic process, again we can write it as so V1 by V4 is equal to T2 by T1 raised to, so from these two equations we can write V3 by V4 is equal to V2 by E1. So we get the efficiency equation. And we have already seen that a Carnot engine is a reversible engine, and it is the only reversible engine which is possible that works between two reservoirs at different temperatures. So we have seen that each step of the Carnot engine in a previous picture. This will amount to taking heat Q2 from the cold reservoir at T2 during work W on the system and transferring heat Q1 to the hot reservoir. That will be a reversible refrigerator. Okay. So now let us see what the important result. We can call it as Carnot's theorem sometimes. Okay. That is, working between two given temperatures T1 and T2 of the hot and cold reservoirs respectively, no engine can have efficiency more than that of Carnot engine, and the efficiency of the Carnot engine is independent of the nature of the working substance. Okay, no other refrigerator can have the efficiency greater than this Carnot engine, and this efficiency of the Carnot engine is independent of the nature of the working substance. Okay, to prove that result A, that is working between two given temperatures T1 and T2 of the hot and cold reservoirs, no engine can have efficiency more than that of the Carnot engine. You just imagine a reversible engine R and an irreversible engine I working between the same source, that is hot reservoir, and sink, that is cold reservoir. So let us couple the engines I and R in such a way that I acts like a heat engine and R acts like a refrigerator. Okay. So let I absorb heat Q1 from the source, deliver work W, and release the heat, that is Q1 minus W, to the sink. So we arrange so that R returns the same heat Q1 to the source, taking heat Q2 from the sink and requiring work W is equal to Q1 minus Q2 will be done on it. Now, if you consider in terms of efficiency, reverse is less than the irreversible. If R were to act as an engine, it would give less work output than that of I. That is, if we can say W will be less than W dash for a given Q1, with R acting like a refrigerator. That is, Q2 is equal to Q1 minus W, Q1 minus W dash. So, on a whole, we can write, isn't it, from the cold reservoir and delivers the same amount of work in one cycle without any change in the source. This is against that Kelvin Planck statement of the second law. Hence, n that Ni greater than Nr is wrong. No engine can have efficiency which is greater than that of the Carnot engine. A similar argument can be constructed to show that a reversible engine with one particular substance cannot be more efficient than the one with using another substance. See, the maximum efficiency of a Carnot engine is independent of the nature of the system performing the Carnot cycle of operations. Thus, we are justified in using an ideal gas as a system even in the calculation of efficiency of a Carnot engine. Okay. The final remark shows that in a Carnot cycle, we can write Q1 by Q2 is equal to T1 by T2. Okay. It is a universal relation which is independent of nature of the system. Q1 and Q2 are heat absorbed and released isothermally in a Carnot engine, and it can be used as a relation to define a universal thermodynamic temperature scale which is independent of any particular properties of the system which are used in the Carnot cycle. Okay, for an ideal gas as a working substance, this universal temperature is same as the ideal gas temperature. This is what I just explained. An irreversible engine which is coupled to a reversible refrigerator. Okay, the diagram is shown in this particular.